Hello everyone, and thanks for watching Edupedia World videos. So in this session we'll simply look at some of the real life examples of reversible reactions. Okay, so we'll look at some industrial equilibria, that is some important examples of reversible reactions which are being used in industries all over the world, or which have been used in the industries in the past. Okay, we'll also look at the effect of pressure or temperature, okay, or concentrations on such equilibrium. Okay, so let's start with the Haber's process, one of the most common processes, okay, and one of the most important process. It is used for formation of ammonia. Okay, ammonia is used in making fertilizers and various other things. All right, and for that we need to have Haber's process. Okay, so the equation for the Haber's process is as follows, that N2 nitrogen combines with hydrogen to reversibly form ammonia gas. Okay, all the reactants and all the products are gaseous in nature over here. All right, and the balancing can be done by us. Let's say we balance it in this way. Okay, 1 mole of nitrogen combines with 3 moles of hydrogen to form 2 moles of ammonia gas. Okay, so for this reaction delta H value is around minus 20 kilocalories per mole. Okay, so this means this reaction is basically an exothermic reaction because delta H value for the reaction is less than 0. Okay, we also use a catalyst in this reaction. Okay, so we'll come to that. For now, if we look at the stoichiometry of this reaction, the stoichiometry of the reaction suggests that delta Ng, okay, that is the stoichiometry of products minus stoichiometries of reactants, is 2 minus 4, which is minus 2, that is less than 0. So for such a reaction, if my goal is to form more and more ammonia, that is my goal is to form more and more product, or my goal is to achieve forward direction reaction more than the backward direction reaction. So to do that, okay, what do I need to do? Should I increase the pressure value or should I decrease the pressure value? It's pretty simple. Since delta Ng is less than 0, increasing the pressure will shift the reaction in forward direction. Okay, we have already seen this effect of pressure on chemical equilibrium. Okay, so this means that for Haber's process, high pressure will be preferred so that more and more ammonia can be formed because delta Ng is less than 0. Okay, whereas if you look at the exothermic part of the reaction, that is delta H is less than 0, we realize that okay, this reaction releases heat upon forming ammonia gas. Okay, that means increasing the temperature will shift the reaction in backward direction. Hence, we would prefer to keep the temperature at lower values. Okay, so low temperature will be preferred so that the reaction shifts in forward direction and forms more and more ammonia. Okay, so this Haber's process, because delta H is less than 0 and delta Ng is also less than 0, is favorable at low temperature and high pressure. Okay, but the thing is, usually for chemical reactions, okay, this is pretty much true that at very low temperature their rate of reactions become very low. Okay, this is because of something called activation energy, which you will study in class 12th. Okay, because of that low temperatures are not particularly favorable. Okay, so this is a dilemma over here. Okay, Le-Chatelet principle says that low temperature will form more and more ammonia, but activation energy tells us that low temperature usually kind of stalls chemical reaction. It kind of decreases their rate of reaction. Okay, in fact it might even decrease the yield of your product itself, not just rate. Okay, so that is why we don't want to keep temperature very low, but we don't want to keep it high as well. So neither low nor high. Instead of keeping temperature very low, we keep it at moderate values. Okay, so for usually all chemical reactions where low temperature is preferred, okay, instead of keeping the temperature very low, usually, not always, okay, usually we'll keep them at moderate values. So moderate temperature and high pressure will help us synthesize more and more ammonia from the given amounts of nitrogen and hydrogen. Okay, because we already know that since it is a reversible reaction, not all of nitrogen and hydrogen can be converted to ammonia. There will always be a little bit, at least a little bit amount of reactant left over. Okay, but we want to minimize that amount of reactant left over. So to minimize that amount of reactants, we will keep high pressure and moderate temperature values. Okay, and obviously if you put more and more nitrogen, if you supply more and more hydrogen, that will also shift the reaction in forward direction, increasing the concentration of reactant and hence forming more ammonia. Another way is to accumulate ammonia, okay, in a different container. That is, as soon as the ammonia is being formed, okay, this is your reactants, nitrogen and hydrogen, they will combine here to form ammonia. If there is a way that we can simply separate out ammonia as it is being formed, okay, this will basically result in decrease in concentration of product at equilibrium. Decreasing concentration of product shifts the reaction in forward direction. Hence, if we can separate out ammonia from here, if that is possible, then even that will shift the reaction in forward direction and help us in synthesizing more and more ammonia. Okay. Also, we want to achieve this yield, okay, this yield or this amount of product, okay, that is ammonia, at a faster rate. I know that I'm going to get 10 moles of ammonia ultimately, but instead of having this 10 moles of ammonia after 3 hours, I want to ensure that I get 10 moles of ammonia after just half an hour. So how can I do that? By establishing the equilibrium sooner, by completing my process sooner. Okay, and what helps to establish the equilibrium sooner? The increasing rate of reactions. Okay, so I can increase the rate of reactions by using a catalyst. So this reaction is also, okay, done in presence of various different catalysts. One of them is molybdenum. Okay, it is a commonly used catalyst for this process. There are also other catalysts, okay, like iron, okay, which we can use for this Haber's process. Okay, so though catalyst will not change the state of equilibrium, it will increase both forward and backward rates equally, but it will definitely help us achieve our final product sooner. Okay, let's take another example. Okay, you have to memorize all these examples, Haber's process and the others which we are going to study. They are important both from your school exams perspective and even from JE or medical exams perspective. Okay, in your competitive exams, these names, Haber's process, okay, the next one which we are going to study, contact process, these directly come in your exams. You have to even memorize the chemical reactions for this equations, and also whether they are exothermic or endothermic in nature, and what temperature and pressure values will shift the reaction in forward direction. Okay, all this you have to memorize. That is why we are studying these processes, though they are quite common and you can find them pretty much in all the literatures or textbooks you might refer to. So contact process is basically a process used for synthesizing sulfuric acid, that is H2SO4. Okay, so we are not studying the complete process, we are just going to focus on an important reaction, okay, an important reversible reaction of this process, okay, which is the formation of SO3. Okay, so this reaction, synthesis of sulfuric acid, that is by using contact process, goes through, okay, a reaction in which SO2 gets oxidized to reversibly form SO3. Okay, this is kind of the key reaction in this whole process. Okay, and this key reaction is basically a reversible process, okay, which once again has a delta H value less than 0. Okay, delta H here is around minus 45 kilocalories per mole. Okay, so this again, okay, is an exothermic reaction. Alright, and also if we look at the delta Ng value, that is the stoichiometry of products minus stoichiometry of reactants, is again less than 0. Okay, it is 2 minus 3, okay, which is basically minus 1 less than 0, and exothermic reaction because delta H is less than 0. So once again, since delta Ng is less than 0 and delta H is less than 0, so just like Haber's process, this reaction will move in forward direction, that is, it will form more and more product SO3, which can later be converted into sulfuric acid to get our ultimate product. Okay, so more and more SO3 can be formed by decreasing the temperature, by keeping very low values of temperature, and by keeping very high values of pressure. Okay, but once again, since low temperatures are not preferred for any kind of chemical reactions usually, okay, so we will instead keep moderate temperatures. Okay, so temperature value here are kept around say 500 degrees centigrade. Yes, they are considered moderate values. Okay, in industries even that is moderate, and pressure values are high. Okay, not as high as in Haber's process. In Haber's process we use pressure values like 3 atmosphere. Here we'll use it like 1.5 to 2 atmospheres. All right, but yeah, they are relatively high, so that more and more SO3 can be formed. Okay, and once again, to attain the equilibrium, okay, to attain this position of equilibrium, when we have already obtained as much product as we can possibly obtain from a reversible reaction, we will also use a catalyst here. Okay, the catalyst can be, once again, there can be more than one kind of catalyst which can be used in this process, but the most common one is V2O5. Okay, divanadium pentoxide. All right, so once again, you will also have to remember the catalyst being used in this process. Okay, it is all going to be part of your inorganic chemistry, but we are studying over here because these are basically reversible chemical reactions. Okay, and also if we can use this SO3 somehow and consume it or remove it from the container, we are basically decreasing the concentration of product, and hence even that will shift the reaction in forward direction. So let's look at one last example. Okay, this is the Birkland Eyde process. It is basically used for synthesis of nitric acid. Okay, though a new process has come up now. Okay, Birkland Eyde process is not so common as it used to be. Okay, before it was the most common, okay, or most used method for synthesizing nitric acid, not so much anymore. Okay, now we use different methods. Okay, an Ostwald process might be more common than Birkland Eyde process. Okay, but anyways, in this process the key reaction is actually where nitrogen reacts with oxygen to reversibly form NO. Okay, and this NO is later on converted to nitric acid by other different reactions. Okay, but this is the key reaction which determines the rate, okay, and the yield and the extent of your whole process in which you will be synthesizing the nitric acid. Okay, so for this reaction, once again, delta H lies in the neighborhood of minus 40 kilocalories per mole. Okay, so here also delta H is less than 0, that means it is an here delta H is plus 40, in the neighborhood of plus 40 kilocalories. So this is an example of endothermic reaction. Alright, so endothermic means delta H is greater than 0 over here. Okay, if here delta H is greater than 0, this means heat is being absorbed along with your reactants to form the product. Okay, also if you look at the delta Ng value is equal to 0 here. Okay, stoichiometry of product is 2 and the stoichiometry of reactants is also 2, and hence delta Ng is equal to 0. So what kind of temperature and pressure will help me increase the yield of my product? Okay, so this is my product NO. Alright, so that I can form more and more nitric acid. So since reaction is endothermic in nature, it is absorbing heat, so keeping high values of temperature, okay, keeping temperature at high values might help me form more product. Okay, whereas since delta Ng is equal to 0, pressure, whether it is high or low, will have no significant effect on the formation of product. Okay, so here pressure values we won't worry about because pressure does not change the state of equilibrium as delta Ng is equal to 0, so we will not Think about it. But temperature needs to be kept high because it is an endothermic process. It absorbs heat, so increasing the temperature will help it in moving in forward direction. Okay, so temperature in this process is kept around 1500 to 2000 degree centigrade. Okay, this is high temperature in industries. All right. Okay, and once again you can obviously use catalyst here as well. Okay, but we don't need to do that. Okay, you don't need to study it in so much detail because this process is not being used anymore. Okay, in inorganic you will study something called Ostwald process, which is now more commonly used for synthesis of nitric acid. Okay, there are also other examples like hydrolysis of simple ester. This is also quite common. Industrial equilibria. Okay, and this is also a a bit of a unique equilibrium. Okay, not so unique but different from what we have studied, because in this, okay, in hydrolysis of esters, what happens is all the reactants and products are in liquid phase. Okay, we have rarely seen such an example. Okay, in most of them we have aqueous conditions, okay, or we have gaseous conditions. Okay, but here every reactant and product is in liquid state, pure liquid state, you can say. Okay, so this makes it kind of unique. All right, and there is Ostwald process, which you will study in inorganic. Okay, there are also some real life examples like transport and exchange of oxygen and CO2 in our body. Okay, when we inhale oxygen, all right, it gets attached to our molecules in blood. Okay, and that blood takes it everywhere to all the other cells of our bodies. Okay, and from there it takes back CO2. Okay, and that CO2 is exhaled out. Okay, this is not a very precise picture obviously, okay, but a crude picture of what happens, okay, when we inhale and exhale. Okay, so even that, okay, taking in oxygen, exchanging it for CO2 and releasing CO2, okay, this transport and exchange is also okay accompanied by various reversible reactions. All right, so even the concentrations of oxygen, CO2 in our blood determines how much, okay, can we breathe in, how much can we breathe out. All right, all those are governed by the Le Chatelier principle, which we have studied basically. Okay, so in the next session we'll look at physical equilibrium. Okay, until now we are mainly focused on chemical processes. Okay, we'll also look at the application, okay, of all this effect of pressure, temperature, volume on some physical equilibrium. Okay, so until next time, and once again thanks for watching Edupedia World video.